Welcome to Course 101, TiDB Technical Essentials. This is Module 6, TiDB HTAP Overview. My name is Jeff, and I am your instructor for this module. After completing this module, you will be able to describe HTAP technology, understand TiDB HTAP architecture, and understand HTAP core features. In 2005, Gartner proposed the concept of the hybrid transactional analytical processing database. Today we call this the HTAP database. In 2014, Gartner clarified its definition. HTAP databases support OLTP and OLAP use cases. First, let's take a look at the left-hand side of the diagram. OLTP functionality includes row-by-row format. Generally, a row store is used to support real-time updates, supports high concurrency, and it requires high consistency. Insert, update, and delete. This means queries are typically targeting a small amount of data. It isn't listed on the diagram, but these queries must be fast, milliseconds fast. If you look to the right, you will see OLAP. OLAP functionality includes row-by-column format. This use case requires a column store. Well, require may be a bit strong, but analytic databases usually use a column store. Next we have low concurrency. This one is mostly select large volumes of data. OLAP queries commonly scan vast amounts of data. Sometimes the data may be scanned multiple times by a single query. Now, let's take a look at the overlapping area in the middle. This is where HTAP lives. It spans both areas. For example, our daily payments and transfers are OLTP business, and reports and real-time statistics belong to OLAP business. HTAP refers to a database technology that can support both OLTP and OLAP use cases. So, why do we need HTAP databases? We've covered this in multiple places, but this is a great time to tie it all together. Let's look at traditional OLTP and OLAP business solutions. The left-hand side of the diagram shows OLTP databases. Recall, they support row-based storage. Data will be extracted from the OLTP systems, then, using ETL processes, it will be loaded into the OLAP systems. These systems include data warehouses or data lakes. This data is used by the business for analytics use cases. Later, the data may be processed and extracted from the OLAP database and returned to the OLTP database. Look at the right of the diagram. Here you have data marts, yet another use case. From what I just described, it's easy to see at least two problems with traditional solutions. The first, by the time the data lands in the OLAP database, it is likely out of date. The second, data warehouse, data lakes, data marts, so many copies of the data. How do you know which one is correct? There is an additional problem that just hit me. The multiple database environments and ETL tools cost a lot of money. With an HTAP database, you can do this in a single environment. This greatly reduces the cost of ETL tooling and programming. Based on our definition of HTAP and the challenges it overcomes, we have the following requirements for HTAP databases. The first requirement is scalability. Due to the large amounts of data, distributed storage is a solution for some NoSQL databases, especially for OLAP use cases. However, due to the need to simultaneously support OLTP and OLAP use cases, we need to have a robust storage solution that can handle both of these use cases. Next, OLTP and OLAP use cases are supported by a single environment. Due to the different characteristics of the two use cases, it is necessary to support both row store and column store. However, OLTP requires high concurrency and guaranteed consistency, and OLAP requires high performance data scanning. How do we ensure that the two do not adversely affect one another? Finally, real-time data analysis is a huge requirement. We need an environment that avoids the "my data is out of date because I had to copy it to a million systems" problem. In summary, A system that conforms to the HTAP scenario must be able to meet the above 3 points in order to truly solve the OLTP and OLAP digital transformation problem. This diagram shows the HTAP architecture of the TiDB database. We have seen that TiDB server, PD, and TiKV have not changed, and the data is stored in TiKV in a row storage manner. The change is that TiFlash is added to the storage cluster. The TiFlash node accesses the multi-raft group using raft learner and synchronizes the data using quasi-real-time synchronization. When the data is synchronized to TiFlash, it will be decomposed from row format into column format. We will introduce TiFlash in another module. For now, it is enough to understand that TiFlash has the following capabilities. 1. Columnar store. 2. Guaranteed quasi-real-time synchronization of TiKV data. 3. Consistency of data. The data is consistent between the row store and the column store. And 4. Smart selection. The TiDB server optimizer chooses where to send the query, columnar versus row-based storage. You don't have to do that. In addition to TiFlash's columnar storage, the TiDB database also supports MPP computing architecture on TiFlash. This plays a role in the acceleration of aggregation style queries. First, TiDB via TiKV and TiFlash components have both row store and column store. Row store TiKV supports real-time updates based on primary keys. TiFlash is a replica of the data stored in TiKV. OLTP processing is isolated from OLAP processing. Second, smart selection. In a complex environment which combines point queries and range scanning, the cost-based optimizer effectively chooses where to send queries, TiKV or TiFlash. And finally, MPP architecture. MPP enables acceleration of aggregation and connection operations on TiFlash. It's important to note that this can only be performed on TiFlash. In the MPP architecture, the TiDB server acts as a coordinator, and each TiFlash has a column store region and participates in the calculation as an MPP worker. There are 4 main points. They are: 1. MPP is suitable for join and aggregation operations with large amounts of data. 2. All MPP calculations are performed in TiFlash node memory. 3. Currently, only equivalent connections are supported. And finally, the enforce_MPP parameter helps verify that the SQL statement can use MPP. Take a look at the query in the bottom left-hand side of the diagram. Notice that it is a select count star query. The from clause lists 2 tables, order and product, so we know there's a join involved. In many databases, all the data will be returned to the central process and executed. Thankfully, that is not what happens in TiDB. The first thing to notice is that TiDB's server's cost-based optimizer chooses to use TiFlash to perform this query. The second thing to notice is that the filtering where predicates are pushed down to the TiFlash components. Remember, this is MPP, so there are multiple machines. This leads to highly parallel processing. Each TiFlash node exchanges data with other TiFlash nodes. The goal is that the data to be joined together will land on a single TiFlash node. Next, the orders table is joined with the products table on each TiFlash node. The data is exchanged again, this time in order to get the hash value of the state column of the order table. The state column is used in the group by clause. Next, the data is aggregated on each TiFlash node. Finally, the aggregated results are returned to the TiDB server. The TiDB server summarizes them. Then the count value is returned to the user and SQL processing is complete. Let's summarize the 2 common TiDB HTAP scenarios. The first scenario is the mixed workload scenario. In this scenario, the TiDB database hosts the OLTP online service performed by TiKV, while the TiFlash column store engine offloads and accelerates the real-time analysis services. To the left of the diagram, we see an app server running online business, reporting, business intelligence, and dashboard. TiDB is powering these applications. To the upper right of the diagram, we see that TiFlash handles the real-time analysis for the reporting, business intelligence, and dashboard applications. Scan down the right side of the diagram. Because of their OLTP characteristics, TiKV handles the online business application. There are more complex business scenarios documented on the official TiDB website. Take a look. The second scenario is streaming. Streaming use cases have the following requirements. 1. Online services are updated in real time and require change data capture components to synchronize the updates to the analysis data stores. 2. The analytics data stores need to be real time and able to synchronize changes to the online business data. 3. The analysis data store provides a SQL interface for analyzing queries. Our requirements demonstrate that TiDB database is an excellent choice for this scenario. We have covered a lot of material during this module. I feel confident that we have met all of the objectives defined at the beginning of this module. First, we can describe HTAP technology, we understand TiDB HTAP architecture, and we understand HTAP core features. Thank you for taking the time to view this module. We hope you enjoyed it and have learned a lot.